Yeah, so my name is Edgardo Sepulveda. I'm coming from Chile. Right now, I'm doing my PhD. I'm a PhD student at the University of Arizona. My PhD is in environmental engineering, but I've been working on the optical properties of ice clouds, the radiative impacts of the high clouds in the atmosphere, under supervision of Professor Sylvia Sullivan from the University of Arizona. So yeah, I have a previous background more focused on Antarctica and Antarctic clouds when I was in Chile at the University of Santiago, but now I've been just moving to more tropical regions, studying high clouds in tropical regions. So yeah, this talk is about the sensitivity of cloud radiative heating, specifically ice cloud radiative heating, and how these radiative heating rates will respond to different optical properties of the ice cloud. So I will to show you a review of some idealized single column tests that we've been doing, also some applications on high resolution modeling like ICON. So yes, you probably already know this. Many of you, I understand you've been doing some air flight campaign, collecting, for example, ice samples from the clouds, and you know that you can find many different ice crystals, different geometries or habits in the ice clouds. So hexagonal columns, boulder rosettes. So the problem is like how we can include this information in current modeling, right? How can we? What will be the impact of including more complexity on the optical properties of the cloud and the radiative properties? So yeah, you already know that there are many different shapes of ice crystals, and this ice crystal will change the optical properties of cirrus clouds, of top ambient clouds. And yeah, that will change the transmission or the reflection of shortwave radiation from one side, and at the same time, this ice cloud and the ice crystal of the high cloud can absorb more or less long-wave radiation coming from the Earth's surface and emit more or less long-wave radiation. So this is the already known like radiative properties of high clouds. And there have been some study try to understand what is the impact of including maybe a more realistic approach, including more ice crystals in the modeling, more complexity. So many studies have been focusing on the cloud radiative effect, for example, at the top of the atmosphere. And in general, including more ice complexity, it will result in shortwave, mainly shortwave cooling at the top of the atmosphere, specifically tropical regions. So the thing is, many of the studies have been focusing only on the cloud radiative effect, of course, because it's easier to evaluate, for example, comparing with satellite measurements. So yeah, we know that the cloud radiative effect from many clouds, specifically ice clouds, can cool the atmosphere by reflection and can at the same time warm the atmosphere by absorbing the long-wave radiation. So this balance that we studied by evaluating the cloud radiative effect is important, but also we want to understand what will be the radiative effect inside the cloud, or what will be the vertical distribution of this cloud radiative effect. So that's why we'll be focusing on this other property, which is the cloud radiative heating rate, which is a flux divergence, or divergence of the cloud radiative effect through the atmosphere. So this is interesting to study because, well, if you study the cloud radiative heating rate, specifically nice cloud radiative heating rate, you can find a common heating cooling dipole, right? So you can see some warming in cloud heating, right, inside the cloud, from the bottom to inside the cloud, and because of absorption of long-wave radiation. But at the same time, you can find some negative heating rate or cloud top cooling because of emission of long-wave radiation. So this magnitude, the magnitude of these heating rates will determine different climate situation, or even weather situation. For example, tightening of the Hadley ascent. There are some studies that I've been correlating the magnitude of the heating rate with amplification of El Nino or the oscillation of ENSO oscillation. And there are also some studies that are trying to link how the heating rate will determine precipitation. Sometimes higher heating rates or higher magnitude in the heating rate can produce a weakening in precipitation, or the opposite, diminishing the heating rate can enhance precipitation. And so, yeah, this is like a new, no, I would not say new, but it's other approach to study how the radiative interaction of clouds will impact the other consequent weather patterns. So the problem is, yeah, tropical cloud radiative heating can change between different products, different modeling products, different satellite products, enhancing some heating and in-cloud heating, or diminishing or enhancing the cloud top cooling. In fact, microphysics can change also the different heating rate magnitudes. If you start to change different microphysics settings in your modeling, for example, you can enhance or diminish the heating rate peak. So the question is how the cloud-radiative heating will change in terms of ice complexity. What happens if we include ice complexity? Well, I already showed you that some previous work has been, in general, shows a diminishing of the cloud-radiative effect. Most work focusing on the shortwave radiation. In this case, we want to study how the cloud-radiative heating rate will change if we start to increase the ice complexity level, ice crystal description. So, yeah, the approach is we use studying the different ice optical schemes available, and so maybe you already know, different models, even satellite measurements use different ice optical schemes, which are these optical schemes are an attempt to represent the optical properties of ice crystals in clouds. So depending of what type of ice crystal do you have, I will give you the optical properties of the ice cloud. That means the extinction coefficient, which will be depending on the scattering and absorption, and the magnitude of the scattering and absorption. Well, we already know the ratio. That information is given by the single scatter albedo. So we know, for example, if an ice cloud has certain number of particles, or certain size of particle, or what kind of geometry, the extinction coefficient can diminish or increase. That will change the capacity of the cloud to absorb radiation, shortwave radiation, for example, to scatter shortwave radiation, sorry, and sometimes can absorb more or less long-wave radiation. And another important parameter that's been included in some studies of the optical properties of the clouds is the symmetry parameter, which just is telling us what is the direction of the scattering radiation. Sometimes can be more backscattering, enhancing the reflection by the cloud and diminishing the transmission of radiation through the cloud. At the same time, it can diminish the absorption of radiation by the cloud or enhancing other times. So all of these parameters are given by the optical schemes, depending of what geometries, size, or what number concentration of ice crystal do we have inside the cloud. So yeah, the test that I'm going to show you use mainly 3 schemes. I'm gonna explain, well, I will show you 4 schemes, 4 different schemes. So one of the most used one, or you can find mainly in most of modeling of Fourier transfer model, is the full scheme from the 90s. Probably you already know this one, or you're been using this one. So the full scheme tried to produce these optical properties of the clouds based on the size of the ice crystal, and assuming that all ice crystals are only hexagonal columns. So the full scheme was distributed in 2 different publications, one for the a parameterization for the short-wave radiation and for the long-wave radiation. I will call these 2 papers just as the full scheme, just full. And there have been different attempts to increase complexity, try to include more ice crystal, more geometries, right? For example, the Baran schemes, they try to create an ensemble distribution of shapes, starting from the basic one, which is the hexagonal column, including Boole rosettes and aggregates. And there we have the E scheme in 2013 that include 9 different habits, including hollowness and also surface roughness. So we can consider like that scheme like more complex relative to the full scheme. And finally, I'm putting this in the last step, is the update of the 2014 scheme. So Baran developed a new scheme in 2016, which assumed the same ensemble from Baran 2014, but now it includes another parameter, which is temperature. So we can classify, or we can create a hierarchy of ice complexity from one side, but at the same time, what are the inputs, or what are the parameters that we can use to compute the optical properties of the ice crystals. So full scheme and E-scheme base their parameterization only on size. Full scheme is a simpler, we can call it a simpler scheme, and E-scheme is a more complex, include more other characteristics of the ice crystals. But Barn scheme, in contrast, it based his parameterization on ice-water mixing ratio, and the Barn 2016 includes temperature in the like in the list of parameters. So that create a big change in the calculation, as I will show you. This so the test that we've been doing, I'm going to show you two parts. The first part is a list of idealized single column simulation. So we create different types of ice clouds. We change temperature of the cloud or altitude of the cloud, geometrical depth, and ice water path of the cloud, to see how the cloud-radiative heating rate will respond to this changing, and also how this different ice optical scheme will try to compute these different sensitivities. So we're using the EC-RAD radiative transfer model, which is the relative new radiative transfer model that's been used in the European Center Modeling Weather Forecasting System. And we include the EC-RAD like an offline simulation. At the same time, we include EC-RAD in high resolution or storm resolving modeling like ICON. So yeah, the first sensitivity test that we'll be developing is studying the heating rate of an ice cloud. We change the ice optical schemes in the ice cloud. For example, starting from the full scheme, which is only hexagonal. We change the scheme to compute the radiative properties and the heating rate of the ice cloud, for example, improving more complexity by changing the ice optical scheme. And at the same time, we, for example, moving the cloud to a higher altitude, and to study how the heating rate will respond to a higher altitude, or in other words, moving the cloud to a colder environment. We'll be changing the geometrical depth of the cloud also, and see how the heating rate responds. We change the concentration, or the ice water path, the number of concentration of ice crystal in the cloud in terms of ice water path. And also, if we have time, we will see if I can show you this, but to see what's happening if we change the size of the ice crystal, how the heating rate will respond, and how the different ice optical scheme will retrieve this information. So we can think this test like different slider. So for the first test that I'm going to show you, which I think is the best approach to start explaining this, is how the ice cloud heating rate respond when I change the cloud temperature. So for now, I fix the geometrical depth. We're going to start at a cloud of 1.5 kilometers depth, an ice water path of 30 grams per square meter, and we're assume ice crystal of 30 micrometers. And we're going to change the optical scheme while we change the temperature of the cloud. So these are the input profile that I'm using to the offline simulation with EC-RAD. So while, for example, I decrease the temperature of the cloud, at the same time, it's like we're moving the cloud to a higher altitude, and you can see how the ice-water mixing ratio start to increase, because I want to try to fix the ice-water path. So fixing the ice-water path at a constant value does mean that I will have to increase the ice-water mixing ratio while I move the cloud, or we transport the cloud to a higher level. So to try to summarize this result, we developed like a matrix visualization of the heating rates. So for example, in this figure that I'm going to show you many of these figures from now. So each column in this figure is one is one simulation, one idealized or single column simulation. And you can see, for example, here, the cloud located at approximately 10 kilometers, or the temperature of the cloud is located at a temperature of 236 Kelvin, approximately 10 kilometers. So when we compute the fluxes and then the heating rate, you can see the heating rate profile here. And yeah, in this case, this is the shortwave cloud-radiative heating. And we see a stronger shortwave heating at the top of the cloud because of absorption of shortwave radiation. The solar zenith angle, we fixed solar zenith angle in this test. So we're using a zenith approximately 53 degrees. So yeah, we see the highest heating at the top of the cloud. But the important thing of this matrix visualization, or the most interesting thing, is you can see what happened when, for example, I move the cloud, I transport to the cloud to a higher altitude or lower temperature, and you can see how the heating rate profiles start to change and have reaching a maximum point at colder temperatures. So decreasing, this is equivalent, or this is happening because by moving the cloud to a higher altitude, the density of air is diminishing, and that is producing an increase of the shortwave heating. So yeah, we can see a similar amount of shortwave absorption at the cloud top, but now relative to a less density air environment, this heating rate increased. So this is the color bar is the Kelvin per day, is the magnitude of the heating rate. The important lines here are the yellow lines. The yellow lines from now on will delimit the range where the heating rate move inside the cloud. Okay, so for example, the minimum heating rate, it will be approximately 1 Kelvin per day, and the maximum point, or the maximum pixel in this matrix visualization is approximately 10 Kelvin per day. This is by using the full scheme, by the way. So similar thing happening in the long wave. You see the common dipole, long wave dipole. If we focus only in one column from now, for example, the right one, that's the cloud layer, we see some heating, in-cloud heating due to absorption of long wave. At the same time, we see some cloud top cooling, so there's emission of long wave radiation, so that's why we have a negative heating rate. We're losing energy, we're emitting radiation there. So this is a common thing, the long wave heating rate. So we are interested to know, okay, how can we represent the change of this heating rate again when we move the cloud to a higher altitude? And you see how the dipole increase, specifically the long wave in-cloud heating is increases when we move to the cloud to a higher altitude. Again, density is the main responsible. And also, yeah, we have a strong heating relative to less density and colder environment. So, yeah, this is something that some people already know, which is people that study the heating rate, how this is going to change. And finally, well, we can compute the net cloud-radiative heating. And you can see during the day, this is like a day scenario. You can see how at lower altitude, the component that dominates is the long wave. You can see in the net radiation, the common dipole that is coming from the long wave radiation. Again, absorption at the bottom, or in-cloud absorption, and cloud top cooling. But at higher altitude, the short wave absorption can dominate during the day. So that way you will have pure heating through the whole cloud layer. And the interesting point now is, okay, what happens if we change, for example, from the full scheme, those are the results that I already showed you, and we change to another scheme, a more complex. What happens if we include more complexity of ice crystal? So all schemes will show you the same patterns that I showed you before, but there's some slight difference. So in the shortwave cloud-radiative heating difference, keep in mind now that we are just showing you the difference of the heating rates. We have a negative values when we compare the E scheme relative to full. In other words, we're saying that including more complexity will help to absorb less radiation, shortwave radiation, and that means that the heating rate will be weaker. So we have more ice complexities producing weaker shortwave heating. So why is that happening? Well, we can try to ask to the optical properties of the clouds retrieved by each scheme. So if you compare, for example, the shortwave absorption capacity from the E scheme relative to Fu, E scheme is absorbing less radiation than the shortwave radiation than the Fu scheme, approximately 18% overall. So that is producing this negative or weaker shortwave heating. So the more interesting stuff happened when for example, study the Baran 14 scheme. Remember the difference now is, yeah, we have other kind of complexity of ice crystal, Buller Rosette aggregates, but I think the most important difference or the most interesting one is we changing the input of the parameterization. While Fu and E base their input in size of the ice crystal, now we are changing to ice-water mixing ratio, so we can find different characteristics. So for example, yeah, we can have over almost weaker shortwave heating at the bottom, but when we reach higher altitude or colder environment temperature, we can find some positive, some heating at the bottom of the cloud. This is only the shortwave. So again, we can ask to why we're seeing this heating rate difference, so we can ask to the difference on the absorption component, and also the asymmetry parameter is playing a role here. So as this parameterization or scheme depends on the ice-water mixing ratio, there's a gradient in the absorption capacity. Overall, it's negative. We have less absorption relative to Fu. This is related with the ice complexity, but at the same time, the input of the parameter is changing the capacity of absorption of the cloud through different layers. So we can see that it's more negative, or it's absorbed less in bottom layers, but it starts to absorb more at the higher layer, but still less than the Fu scheme. And in this case, there's an interesting trend in the symmetry parameter. The symmetry parameter can be negative at lower levels, enhancing, for example, backscattering radiation or reflection. But at high altitude, the symmetry parameter start to be positive. That means like we can see an enhancing of forward scattering. So we suspect that a larger D is increasing the chances of the shortwave radiation to be transmitted through the cloud layer and reach bottom layers at high altitude. That can enhance the chances of absorption for the bottom layers relative to Fu. So again, we can do the same test for the long wave cloud heating. When we comparing these two schemes, like the E relative to Fu and Baran 14 relative to Fu, we find relative similar results in the long wave. So we have overall less absorption in the long wave from E and Baran 14 relative to Fu. This less absorption is leading to a weakening of the in-cloud heating and weakening of the cloud top cooling. So remember, this is a difference. So in the absolute cloud-radiative heating rate, we always see heating at the bottom. It's like the red at the bottom and blue at the top, cooling at the top. In this case, we're seeing a weakening of the heating. That's why we see blue at the bottom now, and a weakening of the cloud top cooling. So that's why we see red at the top. We can say, in other words, the cloud top is less negative. It has less negative heating rate, and the cloud bottom has less positive cloud heating rate. This is common for the two scheme. Again, it's a relative negative absorption capacity in the long way also, but the Baran 14 scheme has negative capacity of absorption in the long way component. It has a gradient, but it's approximately centered at the same scheme. So these two schemes are pretty similar. So what happened now if we study the Baran 16 scheme? So now the story is slightly different. So because now we're including Baran 16 is quite similar to the Baran 14 in terms of ice complexity, but now we're including temperature. And you can see, for example, at the bottom layers, when the cloud is located at lower altitude, we can see, again, weakening of the shortwave heating rate and weakening on the long wave heating rate, as I showed you before, probably related with the inclusion of ice complexity by this scheme. But while we're moving the cloud to a colder environment or higher altitude, we have the opposite trend. We have an enhancement of shortwave heating at the cloud top In this case, in the long way, also we have an enhancement of the in-cloud long way heating and in diminution of the cloud top cooling. So, enhancement of the cloud top cooling. So we have more absorption here and more cooling at the cloud top. And this is related with the strong dependence of the absorption capacity both in short wave or long wave radiation by this scheme. It's a strong dependence with temperature. So for example, if we try in the same scenario, we try to compute the absorption capacity in the short wave and long wave radiation, we see how in balance 16 scheme, we have less absorption at lower layer, but higher absorption capacity at higher altitude. And this gradient can be stronger in the long wave radiation. So we have negative absorption at the bottom and higher absorption capacity at higher altitude, again, because dependence of temperature. So we're having like two main results here. Ice complexity, try to diminish the heating rate, right? Diminishing for example, the in-cloud heating and the cloud top cooling, but including temperature, specifically at lower temperature, we have the opposite trend. We have an enhancement of absorption and short wave and long wave heating rates. With this other tests also, for example, changing the geometrical depth of the cloud. In this case, instead of changing the position of the ice cloud with fixed depth, in this case, we started with, for example, in the right column, a really thick cloud, and then start to decrease the thickness of the cloud by having the cloud top temperature fixed. So you can see how this is the heating rate using the full scheme. So you can see how the heating rates start to increase when we have a high thin cloud in the atmosphere in both short wave and long wave radiation. And if we put all this together during the day, the net cloud radiative heating will be overall heating, right? So specifically at the in cloud, because of long wave radiation, we have absorption of long wave radiation, at the same time, absorption of short wave radiation on the cloud top. So this heating rate will be stronger when we have like thin clouds in higher altitude. Again, we can compare the different schemes, how this different scheme retrieve these sensitivities. So by including complexity, we have similar results than before. So we have mainly weaker short wave heating from the complex scheme like E scheme. Again, is more weaker, I say it's weakest at high altitude and thinner clouds. And yeah, similar result for the Baran 14 scheme, but now including ice water mixing ratio is doing a change specifically at thinner high clouds. And if we try to understand what is going on here, why we have an enhanced of short wave heating by using this scheme, we can ask again, what are the scenario of this absorption capacity and the symmetry parameter under this same context by using the same ice water mixing ratio. So yeah, you see like more negative or less absorption at thicker cloud, but this less absorption start to diminish at thinner clouds. So it's still negative, but it's absorbing more radiation. The thinner clouds are absorbing more radiation than the thicker clouds. But there's an interesting one that, again, is a change of the symmetry parameter from more backscattering, more reflection, to more forward scattering. So for the solar sending angle that we're studying, we expect again that there are higher chances that the short wave radiation to be transmitted through the cloud to reach lower levels and be absorbed in those lower levels, enhancing the short wave heating rates. Similar to the long wave, similar to the previous result, if we study the long wave radiation now, we see similar trend in both scheme. Again, overall weaker long wave absorption is resulting in overall weaker heating rates, right? So there's less in-cloud heating and less top cloud cooling. So there's less long wave radiation that should be that's been absorbed by the cloud bottom, and less long wave radiation that's been emitted by the cloud top. There's some slight difference between these two schemes. And again, this slight difference can be related, we can ask to the gradient in the absorption capacity and the symmetry parameter for this scheme. Keep in mind that the E scheme depends only on size, so that's why we don't have a gradient. The absorption will be constant. The absorption difference relative to fluid will be constant through all cloud layers. But the Baran 14 scheme, because it depends on ice-water mixing ratio, we have gradients in these optical properties. And yeah, what's happening now, we switch to a Baran 16 scheme. Again, we have like similar results than the previous scheme, lower or thicker clouds. We can think in thicker clouds at the lower, at the bottom layers, like weakening of the short wave and the long wave cloud-radiative heating. Again, we assume that this is similar to Baran 14 because they're using the same ensemble of ice crystal, but at higher altitude or lower temperature at the top layer of the cloud, we have an enhancement of in-cloud heating. For example, in-cloud long-wave heating and enhancement of diminishing of the cloud top cooling. So there's an interesting thing because if we mix the short wave and the long wave and we study the real one that's coming in the total radiation balance between the two components, we have the net radiation. Now we don't have a common dipole specifically at thick clouds. We have kind of a sandwich where we have like a weakening of the in-cloud heating, but there will be an enhancement of in-cloud heating in the middle of the cloud layer, and at the same time, an enhancement of cloud top cooling. So why is the reason of this? We know that ice crystal inclusion will play a role at lower levels, but the problem is at high altitude, at lower temperature, the absorption capacity in both short wave and especially in the long wave radiation can be enhanced a lot by the temperature inclusion. So, for example, strong long wave absorption relative to the full scheme is enhancing the long wave heating rates at higher altitude. So another test that I want to show you is the ice-water bath test. I'm going to try to do this fast. So in this case, I fixed the geometrical depth at 1.5 kilometers, the size of the ice crystal at 30 microns, and we changed the ice optical scheme. But now we do like two tests at the same time, really. So, for example, when we locate a cloud at this temperature level to 36 Kelvin, we start to increase the ice-water path and computing the corresponding ice-water mixing ratio. So this will be the different inputs in our idealizing simulation with EasyRAD. Then we did the same thing by the next temperature level. So we have this different set of inputs, and we did this 3 times independently. So we took all of this profile independently in the calculation and compared the results. So yeah, again, for example, in this case, now we have different ice-water path levels, and we're studying how the heating rate changed when we're increasing the ice-water path. For the lower, highest temperature level, or the lowest altitude, which is approximately 10 kilometers, this is to 236 Kelvin. So we see how increasing the ice-water path is increasing the heating rate, the short wave heating rates at higher ice-water path, and at the same time increasing the long wave dipole, more absorption of more in-cloud absorption and more cloud top cooling. But again, like I showed you before, we have this different test, 3 independent layers. So we did this computation differently. These are not 3 layers computed at the same time. These are 3 different layers computed independently. We see how, for example, the cloud-radiative heating rate, as I showed you, increased with ice-water path, but also increased with altitude. This is mirroring this is the same result from test 1. But we wanted to see, okay, what's happening if we change the ice-water path also. The most interesting thing here is in the long wave, you can see like the dipole will appear, and the common long wave dipole will be present at ice-water path higher than approximately between 4 and 20 grams per square meter. The dipole start to shift to the right at higher altitude, but it's an interesting result. So please remember this, we have overall heating a lower, overall long wave heating a lower ice-water path, and the common dipole in-cloud heating and cloud top cooling at higher ice-water path. Because when we we take the difference between the schemes. We see now, for example, in the long way, again, like the E scheme, including more complexity, is diminishing the capacity of absorption of long wave radiation, and the final result is less heating, right? So that's why we see the blue in the region, we saw the red in the previous figure in the absolute magnitude. So this is the difference. We have less in-cloud heating and less cloud top cooling, right? Now, it's a more interesting thing in the short-wave radiation, with almost overall weaker heating rates like the previous results, but at really high ice water path, we start to see some patches, some region of enhancement of shortwave heating, and we think that that's related with the positive asymmetry parameter relative to full. So we have more ice crystals here, and also more forward scattering, so that can enhance transmission of shortwave radiation that can reach lower layers in the cloud, lower layers in the cloud layer, and that can enhance absorption and increase the shortwave heating. So yeah, as I showed you before, but the long wave follows the same trend that the previous tests. More ice complexity leads to overall mainly less absorption, less long wave heating rates, and at the same time less cooling rates. When we studied the Baran 14 scheme, we see this interesting trend. For example, now more heating at higher ice water path. Again, this, if we try to ask to the optical properties computed by this scheme, we see how the shortwave, especially the shortwave difference in the asymmetry parameter when we compare Baran 14 against full, the heating rate follows a similar trend. So we have like a positive asymmetry parameter at higher ice water path, more forward scattering, and again, this we think is less reflected radiation, more transmitted radiation through the cloud layer, and that can enhance the shortwave absorption. Similar thing in the long wave component, but keep in mind that the long wave component is coming from the surface at, we can call it like a sourcing angle and a nadir of 0. So it's straight fluxes that's coming from the bottom, and that can create this interesting region that some part of you can have an enhancement of in-cloud heating or the awakening of the in-cloud heating, depending of the ice water context. And when we study the Baran 16 scheme, when we include the temperature, again, now we can see like some enhancement of shortwave heating at the cloud top, specifically at higher altitude, and some interesting region again. So this is again related with the strong absorption capacity by this scheme because of temperature, specifically at a higher altitude. So we have, in this case, an enhancement of the in-cloud heating and a weakening of the cloud top cooling. The long wave absorption is high. The absorption capacity of this scheme, the Baran 16 scheme, in the long wave component is stronger than in the short wave component. So the thing that we try to understand is why we see these interesting shapes when we change the ice water path. You can see some changes. It's not uniform, right? So we think that the answer to that is related with the asymmetry parameter changes. So sometimes enhancement of forward scattering or enhancement of backward scattering, again, in the long wave, for example, from the bottom, can produce this interesting shape. So there's a balance between changing the absorption capacity and the asymmetry parameter capacity at different ice water paths. So now what happens if we apply this scheme in a more realistic context? We try to study the sensitivity with idealized single column simulations, but if we take the same scheme, the same radiative transfer model into a storm resolving model like ICON, for example, in the Asian monsoon region, we can compute the average of the heating rate under a certain context. And in this case, for example, we evaluate the full scheme and the Baran 16 scheme, sorry. This is the net cloud-radiative heating rate. And as I showed you before, at lower altitude, where we have certain ice cloud, the full scheme is higher or absorb more radiation than the Baran 16 or that a more complex ice crystal scheme, I would say. The interesting thing is like including complexity not necessarily will maybe improve the modeling, that depends on the spatial and time context. So you can see how the full scheme, for example, it follows the same trend that the satellite heating rate. Keep in mind that the satellite heating rate also use some ice scheme to retrieve these radiative fluxes. So it's difficult to compare, but it's giving us like a clue of what is the what can be like the most accurate heating rate. Yeah, at the cloud top is the full scheme is next to the satellite, but at lower altitude we can expect why the satellite information has less precision, right? So, but in general, and this is like the takeaway that I want you to take with you, that ice complexity is weakening the net cloud-radiative heating rates. When we include more ice crystal description, we will have, in general, lower heating rate. And we can even try to ask to the previous information, the previous simulation, why we see what we see in a real, relative real context. So for example, in this scenario, we can see what is the temperature profile for in this Asian monsoon context. And we see, for example, the peak of the heating rate, which corresponds to the peak of the ice-water mixing ratio, as I will show you next, correspond to a relative high temperature, 233 Kelvin. So, for example, we can ask to the test of the ice-water bath test, when we compare the balance 16 against full, the net cloud-radiative heating difference, and we say, okay, we can take like this block here, like the highest temperature or lower altitude, to see if it's a correspondence of a match between the idealized single common simulation and the icon simulation. And also we can, for example, ask the ice-water mixing ratio profile. So this is like the cloud profile. And we say, yeah, the highest difference, the highest delta of heating rate corresponds to the peak of the ice-water mixing ratio. But this ice-water mixing ratio to the corresponding temperature and density level, it's taking us to this range of ice-water path approximately. I'm taking now like between 2 and 8 kilograms of ice water over kilograms of air. So that's giving us like this range of ice water path. So we see from the previous test that the bar 16 also enhance the cloud heating rate at higher altitude. At lower altitude is diminishing the heating rate, again, because at this level, the ice complexity is the most important change, and that is diminishing the total heating rate. Okay, there's a small difference between the ice-water mixing ratio because of the microphysical processing the modeling. So because it's taking account some radiative results between the two schemes, and that will result in a slight different ice-water mixing ratio, but it's giving us the range that we can use to test. And this is like a work that I've been doing right now. And to finish the talk, we can see what is the impact of using this optical scheme, not only in the radiative properties, but also in other atmospheric parameters, like I explained you before, for example, in precipitation. And we can see in this case, we are weakening the heating rate by including more complexity, but that is enhancing the maximum precipitation rate that we can compute under this scenario. This is a preliminary result that we have to discuss, maybe checking what is happening with the microphysics also. It's not an easy question to answer, but in general, there are previous work that are explaining that weakening the heating rate can increase precipitation. In our case, we're finding a 7% of increase in precipitation, but this is in accordance with previous work where they say how the heating rate can impact the precipitation. It's not a direct relation, but it's related with the microphysics. It's something that we have been studying. And also there are other implications. For example, from previous talk here in the ACCP Journal Club, CP Club, for example, this is from Adam Sokol presentation. They try to study the ambient hypothesis. It's like how the ambient clouds will evolve or will change in time. So there's an importance of the radiative effect of the cloud. The radiative effect of the cloud, even the heating rate of the cloud, will determine the speed at which the cloud will evolve in time. For example, diminishing the cloud depth or increasing the cloud depth, and try to move to a preferred state, which is like approximately 30 grams per square meter. If we do the similar test, for example, to try to study this hypothesis, by changing the ice optical scheme, we expect that the speed at which this process happen can be increased or decreased depending on the ice complexity inclusion or temperature inclusion in our parameter. So to finish, in general, ice complexity, including more ice complexity in ice cloud, can diminish the short wave and the in-cloud long wave heating, and also the cloud top long wave cooling. More ice complexity is leading to less absorption. It's a less absorption capacity, and also it can enhance sometimes the asymmetry parameter, the forward scattering, and that can result in changing on the heating rate. And this can be stronger, especially in high altitude when we have we want to simulate high clouds in the atmosphere. For example, next to the tropical tropopause layer, we can find this highest sensitivity. This in general for the ice complexity, but also there are other schemes that can include temperature in the parameterization. And in this case, temperature dependent scheme can, and the opposite, enhance the net Cloud-Radiative heating rates, specifically at high altitude or cold temperature environments. So yeah, this is the main takeaway that, again, I want you to keep in your head. So ice complexity can play an important role when evaluating Cloud-Radiative heating rate. And we have to keep in mind that ice complexity or ice crystal description can change in space and time. So depending on the space and time context we have to be careful in which ice optical scheme we should use, depending on what kind of ice crystal do we need. How can we know that? Well, we need more airborne, more flight measurements to have a better distribution or description of the ice crystal in the world. So that's the thing that I want to show you. So thank you for hearing this. I think it was kind of a long talk.